good morning dear student friends, and the course titled Smart Grid Basic to Advanced Technology, and we are focusing on module 10 lecture 4 demonstration of parallel inverter operation in AC microgrid. Now, in this lecture we will see the demonstration of the parallel operation of the inverters, and we will also try to understand the challenges of parallel operation by considering a few test cases. First of all, let us understand why we need parallel operation. From the perspective of renewable energy application, let us say we have a PV plant and we have to further increase the capacity of this plant maybe 2 times, 3 times or maybe any multiple fold. In such a case, we will connect many such inverters in parallel instead of connecting a single large inverter, and sometime it is underutilized. This kind of scenario where inverters operate in parallel can also be seen within a microgrid. When operating in grid connected mode, these parallel inverters simply act as current sources. The figure shown here in the slide represents a PV plant where many inverters are connected in parallel, and each inverter has an LCL filter at its output terminals. These inverters are connected to independent renewable sources represented as DC sources in the figure. In this test bed, we can see two inverters, inverter 1 and inverter 2 are connected in parallel at a point of common coupling formed at MCB. In our earlier demonstration, the inverter output is connected to an L filter to smoothen the current fed to the grid. However, in this demonstration, the two inverters are provided with LCL filters which have a higher attenuation rate compared to the L filter. These two inverters in our test bed have a similar rating. Before we look into the operation of this test bed, let us understand the challenges involved in the parallel operation of the inverters. A single line diagram of a two inverter system connected in the grid through a grid impedance LG shown in this slide. Let us assume that both inverters are connected to independent renewable sources and that both inverters have identical ratings. In this parallel configuration, we can see two components of output current in each inverter. The first component is the interactive current component which flows between the inverters. This current component is equal in magnitude and out of phase with each other. The second component of the inverter output current is the common current that flows into the grid. These common currents are responsible for delivering the power generated in the renewable source to the power grid. The interactive current component basically consists of high frequency oscillations. Also, these currents flow between the two inverters and their frequency of oscillation is equal to the resonant frequency of the LCL filters. Now, we will understand how these two current components, interactive components and common current components are generated. Here, we will now go into the detailed derivation of these two current components. Rather, we will see how these two current components can be represented in terms of basic equations. Using these equations, we will also try to understand what are the scenarios under which these currents are generated. Firstly, let us understand a single inverter system connected to the grid through an LCL filter. In the single line diagram shown, the inverter is represented by a voltage source V01. This voltage is as good as pole voltage or inverter output voltage L11, L21 and C11 are the LCL filter parameters. LG is the grid impedance, whereas VG is the grid voltage source. Here we are controlling the grid side current I21. Since we are using LCL filter, there is a possibility that the filter will resonate. This resonance need to be damped. We are using the capacitor current active damping method to control the resonance. The closed loop transfer function between the output current and the reference current is given by IT1 equal to G1 times I reference 1. Here G1 is the closed loop gain between the error signal and the inverter output current, and its expression is given below, where G1 is given by VO1 upon E times I21 upon VO1. The inverter output current I21 has only one current component. This component flows from the inverter to the grid. Now, let us see what happens if we connect one more inverter in parallel. Here in this figure, we can see two inverters that are connected in parallel. They are represented using the voltage source VO1 and VO2. These voltages can also be called as pole voltages or inverter output voltages. For each inverter, the grid side current I21 and I22 are controlled. Now, let us write the expression of inverter output current with their pole voltage VO1 and VO2. The currents I21 and I22 can be represented in the transfer matrix form as given I21, I22, which is standard actually G11, G12, G21, G22 times VO1 and VO2, and you could see this matrix is because of 2 it is 2 by 2, and however this can be n cross n depending upon the number of inverters that you connect. Where G11, G12, G21, G22 are the elements of the transfer matrix that can be calculated using the superposition principle. Notice here in this transfer matrix, the first inverter output current I21 has two current component. One is I21, which is G11 VO1. This current is due to the voltage source VO1. Similarly, I21 has one more component, and it is due to the pole voltage of VO2, and it is given as I21, which is G12 VO2. I think if you expand this expression, you can see I21, which is equal to G11 VO1 plus G12 VO2. So, from the discussion you can see they are talking about this first component and the second component. Same thing holds good for the second inverter output current I22. Thus, we can conclude that when inverters operate in parallel, there is a possibility that interacting current flows between them in opposite directions. From this, one can infer that there is a coupling among the inverter output currents. From the circuit shown here, we can clearly understand how each inverter output current is having two current components. Using the principle of superposition and considering the effect of one pole voltage at a time, we can write these equivalent circuits. As we have considered identical inverters, the value of the inductors and capacitors in the filter circuits are same for both inverters. Hence, these circuits have symmetry, and so does the transfer matrix shown in the previous slide. Now, we can solve these circuits to obtain the elements of the transfer matrix easily. After solving those circuits shown in the previous slide, we can obtain the value of G11, G12, G21 and G22, the diagonal all the gain matrix. Because of the symmetry that we just spoke about, we will get G11 which is equal to G22, and the diagonal elements which is G12 which is equal to G21. So, what does this indicate now? This indicates that the current component of IT1 due to VO1 represented by G11 and the current component of I22 due to VO2 represented by G22 have identical behavior. That means, there is a similarity between two parallel inverters because of the current component having similar features. These components are the one that actually transfer the power from the inverter to the grid. So, the philosophy of parallel inverter connected to the grid, who is responsible for power transfer is now being understood. Similarly, the current component of I21 due to VO2 represented by G12 and the current component of I22 due to VO2 represented by G21 have identical behavior. These are basically the oscillatory currents flowing between the inverters. So, just to go into detail. So, you have two inverters and we had 4 current components, okay, 2 from each inverter, and 2 components are responsible for power flow and 2 components are responsible for oscillatory currents flowing between the inverters. The elements of G11, G12, G21 and G22 contain two plant transfer function GP and GC, and these two transfer functions are identical except that GC has grid impedance term LG. Additionally, these transfer functions contain the information of resonant frequency points omega r and omega r1, which are without and with grid impedance LG respectively. Therefore, we can now say that the transfer function GP and GC contain the information of different current components present in the inverter output. Further, they also give information on the frequency of oscillation if there is any interactive current flowing between two inverters. After understanding some basics on how inverter output current behaves, now we have come to the final stage of getting the actual expressions for interactive current and common current. In a similar way, we did for the single inverter. Here also we will derive the closed loop transfer function of a 2 inverter system with inverter output currents as the output variables and error signals as the input variables. By doing so and performing some rearrangements in the equations, we can get the expressions for interactive as well as common currents as shown in the slide. Here D is the transfer function from error signal to inverter output voltage VO1 for inverter 1, and the same holds good for inverter 2. Hence, D is identical for both inverters. For more details on the derivation of interactive and common current expressions, students can follow the reference given below. We can make few observations from these two equations. From the interactive current expression, we can see that this current is proportional to the plant transfer function GP as well as the difference between the reference current of the two inverters. Let us suppose that the reference current IREF1 and IREF2 of both the inverters are same. In such scenario, the interactive current will be 0, or in other words, there will be no any interactive current flowing between the two inverters. Only one current flows out of the inverter, that is the common current. Furthermore, as the interactive current is also proportional to the transfer function GP, this current is very much independent of grid impedance LG. Thus, we have seen in the previous slide from the expression of G p. Apart from that, the interactive current is also dependent on D, which in turn suggests that the value of the current control gain is also responsible for the flow of interactive currents between the inverters. Not all the values of controller gains which meets the phase margin and cutoff frequency requirements will eliminate interactive currents. Lastly, if we look into the expression of common current, it is proportional to the transfer function G c, D and the sum of the reference currents of both the inverters. The dynamics of common current of both the inverters are dependent on the grid impedance. What does this mean? It means that if we change the reference current of any inverter apart from the dynamics in the common current of this inverter, there will be the dynamics present in the common current of the other inverter also, which dies out with time. A simple solution to overcome the interactive current is to make sure that characteristic equations of the transfer functions of interactive and common currents will not have any poles in the right half of the S plane under varying grid impedance conditions. Inference. An inverter with LCL filter at its output terminals need to ensure interactive and common current stability when identical inverters are connected. The above scenario is different when there are dissimilar inverters. The problem of interactive and common resonance does not occur in L filter inverters due to their first order nature. Now, let us look into the hardware demonstration of parallel inverters. We will try to replicate the interactive and common currents using the hardware test bed, considering various test cases. In this video, we can see we have two identical inverters, inverter 1 and inverter 2. These two inverters are connected to the grid through LCL filters. The control system of inverter 1 is programmed in Texas TMS 320F28379D launchpad, while the control system of the second inverter is programmed in the Opal RT platform. These are the sensor circuits and signal conditioning boards of the inverter 1, while these are for inverter 2. Further, separate DC sources, one for inverter 1 and the other for inverter 2 are used to form the DC link. These inductors represent the grid impedance used for the demonstration. This MCB forms the PCC, which is further connected to the grid emulator. Now, the inverters in the test bed will be made to inject power into the distribution grid through the grid emulator. Firstly, the inverter 1 is turned on. Once it has started injecting the power into the grid, the second inverter is made to operate. We will conduct two test cases now and the corresponding results are captured. To start with test case 1, in this test case, the reference current of both inverters are set to 5 ampere each. As a result, there is no interactive current flow among the inverters. This can be clearly seen from the waveforms of the DSO. Here, we have captured the voltage and currents of phase A only. The first signal is the PCC voltage. The second signal is the total current of the two inverter systems being injected to the grid, and this is the common current. The third signal is the current I21 and the fourth signal is the current I22. Notice that all the 4 waveforms are stable. Hence, we can conclude that there will be no interactive current flow when the reference currents are the same. Now, we can move to test case number 2. In this test case, the reference current of the inverter 1 is set to 5 ampere, while that of the inverter 2 is set to 6 ampere. So, intentionally they have been made different. Because of the difference in reference currents, we can see oscillatory interactive current flow among the inverters. We can see from the DSO waveform that the currents I21 and I22, that is third and fourth signal, have high frequency oscillation due to the presence of interactive components. The frequency of oscillation is equal to the resonant frequency of LCL filters. Moreover, the total grid injected current of channel 2 is stable. These two test results are in tandem with the analysis performed in this lecture. Thank you.